A very good day, everyone. In this lecture, we'll be considering the interaction of electromagnetic radiation with atoms. And we understand that this effect plays a crucial role in the development of lasers, photodetectors, even electro-optics, and many other modern devices. And since the electromagnetic fields acting on the atom are time-varying parameters, the corresponding Schrödinger equation is a partial differential equation with time-varying components. And this makes the separation of variables method quite inappropriate in terms of finding the solution to the Schrödinger equation with quite a number of time-varying components. And as such, an approximate method is required, for which the time-dependent perturbation theory becomes a possible method. Okay, that is the time. Theory. Okay. Well, before we begin with the time-dependent perturbation theory, to better designate an atom in an electromagnetic field, recall that a dipole usually refers to the separation of charges within a molecule between two covalently bonded atoms or an atom that shares an ionic bond. And an atom in which the center of the negative cloud of electrons has been shifted slightly away from the nucleus by an external electric field contributes an induced electric dipole. Okay? Induced. Hence, it should be noted that the absorption and emission process due to the electric dipole interaction of atoms with EM radiation, or that's electromagnetic radiation, and the related transition probabilities, which we'll be talking about, and the selection rules, may be understood on the basis of the first order perturbation theory. And one of the very interesting properties, or better still, application of the perturbation theory is laser, which is light amplification by stimulated emission of radiation. And for us to be able to see how the time-dependent perturbation theory applies to the electric dipole interaction energy, which we are going to designate as V sub 1 hat shortly, it would be good to provide a proper statement for the Schrödinger's equation for electric dipole interaction of atoms with electromagnetic radiation. So if we consider the electric dipole interaction of an atom with a monochromatic transverse electromagnetic wave with a wavelength lambda long compared to the spatial extent of the atom, it is expected that the electric field of the wave is a known applied field of the form A hat of t being the same as A hat, no, that's vector E rather, A hat, not the operator, but that's the vector, the electric field as a Euler minus j omega t plus vector E intricate Euler j. And it should be noted that this field is not modified by its interaction with the atom. And the Hamiltonian of the atom in the field is of the form H hat, which is the operator, which is the same as H not hat, which is the field, or better still, the energy of the Hamiltonian of the atom in the absence of the externally applied field, plus V sub 1 hat, which is the energy of the electric dipole interaction with the atom, between the atom and the field. That is V hat sub 1 is the electric dipole interaction energy between atom, the externally applied field, by H naught hat is the Hamiltonian the atom, that is the particle, in this case, in the absence the externally applied field. So consequently, the electric dipole interaction energy between the atom and the externally applied field, V sub 1 hat, is given as negative vector P hat dot vector E of t, is the electric field component. And there, the vector P hat is the operator. This is the operator corresponding to the electric dipole operator of the atom. Now, if we consider a single electron, say we consider just a single electron at some r hat equal to 0, assuming that the electromagnetic wave is propagating in the x direction and is polarized in the z direction, then the or better still, the electric dipole interaction term in Schrödinger equation or representation will be given as V1, V sub 1 hat, Zt, since it's polarized in the z direction, being the same as the electronic charge component, Z E sub z of t should be the same as E Z E tide sub z exponential j t plus E Z tide sub z steric conjugate Euler so t j t. So let's assume this is some equation start here. So you recall that for a single electron hydrogenic atom or ion, the corresponding time-dependent Schrödinger equation is given by J H cross d dt psi r hat t, same as H hat r vector t psi r hat t, which is the same as h naught hat r vector energy due to the interaction 0t, which is given here. Psi, which is the wave function. This is going to be the same as negative squared 2m and squared r plus r so t times the wave function. Say this is now, since z and t shows some level of dependence in v hat sub 1, which is the energy of the electric dipole interaction between the externally applied field and the atom, and this equation, equation star 1, therefore becomes impossible or difficult to solve using separation of variables. But if the intensity is too high and the applied electric field amplitude is small compared to the Coulomb field experienced by the electron in the atom, then the V sub 1 hat on the wave function may be considered a small perturbation in comparison with h naught hat. So in other words, this value is way too small in comparison with h naught. If that is so, hence the standard time dependent perturbation theory may therefore be used to figure out an approximate solution to equation star 1, since the effect of the energy acting on that atom relative to the applied field is way too small compared to the energy outside the external field, then we can now present a proper statement for the solution to this equation, for which the time dependent perturbation theory applies, since this parameter, the energy due to the field, is way less than h naught hat. So the time-dependent perturbation theory. Now, this is a powerful general approximation technique for solving the time-dependent Schrodinger equation. And the two requirements that must be met for an approximate solution are that the error in the neglected remainder must be demonstrably small. Like you said, v hat is far less than h naught hat. Therefore, the error in this must be extremely small. then there must be a systemic way to improve the accuracy of the approximate result. So hence, if the effect of the perturbation term, that is V sub 1 R Ct, is small compared to H naught hat, it is assumed that the solution may be expanded in a power series of successive orders of smallness, for which the artifice, say epsilon, or E, is introduced, such that we have a solution for the wave function psi of 1 plus the artifice psi of 1 plus the artifice squared psi of 2 plus the artifice cube psi of 3 all the way to artifice to the power of n psi of n. So let's call this equation star. We already have equation star 1, which is the Schrödinger equation for which we demand a solution. Hence, the effect of z sub 1 hat of zt on the eigenvalues and eigenfunctions of the Hamiltonian h hat are considered in the order of the artifice, smaller than h naught hat, and identified as such by multiplying it by the artifice, which can eventually be set to 1, such that we have the Schrödinger equation given now as the imaginary component j h cross d dt psi, which is the Schrödinger equation, is the same as the Hamiltonian operator acting on the state function, for which the Hamiltonian operator is given as the Hamiltonian of the energy acting on the atom, or better, the energy acting on the atom, excluding the field without the field, plus the artifice multiplied by V sub 1 hat, which is the energy acting on the atom relative to the field times the state function. So let's say this is star 3. Okay. Now, by substituting star 2 into star 3 and equating terms of the same order, term by term, we can obtain a hierarchy of equations of successive orders such that the artifice north is given as j h cross d dt south north minus h naught cross south is equal to 0. This 1 j h cross d dt south 1 h naught hat south 1 same as v hat sub 1 south 1, then artifice squared j h cross d dt psi 2 minus h naught hat psi of 2, the same as v sub 1 hat psi of 1, and then all the way to artifice to the n given as J H cross ddt psi n H hat not psi n same V sub hat psi of n. Okay, so if for instance we call this equation star 4(1), this is our equation star 4, star of 4(2), this star of 4(3), and this equation star 4(4), for instance, then these equations may be solved order by order. Okay, now note that the basic partial differential equations to be solved for every order are always the same in this case, and only the derived, or better still, the driving terms here, only the driving term on the right side, this term here, for which we have the energy relative to the effect of the fields, depends on the solution of the previous order. Okay, so if we are able to solve star for 4(1), then the solution here could be substituted into this, because the solution here, we're able to get this parameter, and then we can plug that into this parameter. Now we're able to get this parameter, and then we can plug that into this parameter, then we're able to get this parameter all the way. Hence, once the 0th order problem is solved, one can in principle solve the nth order equation and find the solution to our third equation here. Okay? Hence, the 0th order equation, which is this, is the unperturbed time-dependent Schrodinger equation. Okay? Because the effect of perturbation is felt by V hat sub 1. Okay? Because that is where we have the artifice added. And you see that it is not included in the 0th order. So it is the unperturbed time-dependent Schrodinger equation. So once it is solved, the driving term V sub 1 hat psi of 0 of the first order from equation star 4, 2 is known. And solving equation star 4, 2 leads to the driving equation V sub 1 hat psi of 1 of the second order equation in star 4, 3, and so on. So in the final solution, the artifice E may be set to 1. And the systematic approximate solution will now become psi, for which we take a limit where the artifice is set to 1. Then you can say psi of 0 plus the artifice psi of 1 plus the artifice squared psi of 2 plus the artifice cubed psi of 3 plus all the way to the plus the artifice of the power of n psi of n. So by terminating the series at the nth term gives the nth order solution whose error, the nth order solution, that's whose error will be n plus 1th order. Okay. So note that the first order solution, according to the above perturbation procedure, leads to the famous Fermi golden rule. Okay. Now, recall that we mentioned that the transition probabilities or probability and the selection rule plays a vital role. So now let us look at the transition probability. Because the point is, should we expose this atom? Let's assume this is the electric field or electromagnetic field, and here we have this atom. There's every tendency that it may be excited to some state N2 or excited to some state N1. So the fact that it has to transit from state to state, it could even be translated to some state N3 or to some state N4 or to some state N0, okay? But now we say start from N1, okay? That's just imaginary. So long this atom could move between states, then we now have to investigate the transition probability within the field. Okay. Okay. Now, in relation to the problem of interaction of the electromagnetic radiation with a hydrogenic atom, if by applying the time-dependent perturbation theory to the equation, the Schrodinger equation stated in answer 1, we obtain the zeroth order and the first order equations in the Schrodinger representation such that the artifice will give us the Schrodinger equation, H cross d dt, like we saw earlier, plus H cross squared 2m lambda squared. Yeah. This is not RT equal to 0. And then the first order given us JH cross ddt plus H cross squared 2m lambda squared. So here this T equal to 0. Okay. So let's say this is our fifth equation, 5-1. This is 5-2. And now, if we assume that the initial condition is at T equal to 0, the system is in the state psi EL of R, that is in the initial state. We assume that is at T equal to 0, that the system is in the state psi EL of R vector. Then psi of north R vector at T equal to 0 will be equivalent to psi of L R T equal to 0, such that we have the same to be the same as psi of L of R, because T is the same as 0. So, assuming we solve the time independent Schrodinger equation given by H cross squared by 2m lambda squared is V of R cross EL of vector in the same as negative EL psi EL recall the solution of the time-dependent Schrödinger equation such that our star phi 1 solution become psi of L naught R vector T with the same psi of EL R vector, the Euler component minus J EL over H cross T. Recall our previous lecture series, the solution to the time-dependent Schrödinger equation. So if we call this our sixth equation, for instance, so call this equation star 6, and then we plug this equation, then we plug this equation into this, then we will get cross ddt cross squared 2m plus squared 3r some form t should be the same as v sub 1 sub el vector, so it's j el cross t. So let's say we have seventh equation. Okay. Now, since this seventh equation, from this seventh equation, the differential operator involves terms of separate independent variables, that is r vector, and t, the method of separation of variables applies. And the general solution by the separation of variables will become psi of 1 r vector t with the same, the sum, say m for CLM 1 t psi em r vector epsilon j e sub m by h cross t. So let's say this is our equation. Now, substituting this eighth equation into our seventh equation, this into this from the left, and integrating over the space coordinates show the expansion coefficient. This, right, satisfies the equation j h cross d dt CLM 1 t is the same as the integral psi m conjugate r vector v sub 1 psi el r vector so j sub m minus sub l divided by h cross t dr. So this is our equation. And by making use of the autonomality condition of the eigenfunction, then this equation 9 is a simple ordinary differential equation whose solution is of the form t same as minus j h cross the integral from 0 to t with integral sine steric m r vector V sub 1 R vector T prime T prime psi EL R vector ER then U J EM minus EL T prime H cross T prime, which satisfies the condition CLM 1 of T equal to 0 in the same as it. Let's say this is our 10th equation. Okay? And for the particular perturbation term of the harmonic type given in our star P equation, right? Then C sub L of 1 of T will be represented as CLM 1 of T, electronic charge, ZLM E tide sub Z 1 minus 7J in L sub omega T divided by H cross L omega plus ZLM tide sub Z 1 minus 7J M plus omega T divided H cross M L plus omega, and this will be approximately so Z L E tide Z to 1 minus epsilon J M L plus omega T H cross L so this is our equation. In the near resonance case, so we're not talking about near resonance case where ML so omega is far greater than ML minus omega and approximately equal to 0 such that omega ML will be assumed to be approximately to omega. Okay, assuming that if we assume now that E sub M is greater than E sub L, where this is the upper level of excitation, high upper state, and this is the lower state. So this has to do with the uppermost state, while this has to do with the energy in the lower state in terms of transition corresponding to the absorption process. Now, to the first order, the former solution of our star 3 equation that satisfies the initial condition is therefore given as state function R of T, which is psi L R vector epsilon J EL over H cross T plus sigma for m not equal to L. So the states are distinct here. CLM 1 of T psi M R epsilon J M over H cross T plus C. But that will be approximately equal to psi L R vector epsilon J EL H cross T plus sigma for M the same as L, electronic charge, ZM times Z, bracket minus epsilon J, omega T divide H cross omega multiplied state function, so M, which is a state function upon state, so minus J sub M H cross T. Okay, so now if we say this is our 12th equation in this case, where ZLM is the same as the integral sine conjugate our vector Z sine our vector dr is the Z component of the induced. Now this is the Z component of the induced electric dipole, or better still, the transition moment. Between the eigenstate psi EL, which is the lower state, and the state function state. Okay, so this 12th equation shows that there's a certain probability that an applied electric field can induce a transition of an atom from its initial state psi EL to some other state psi EM, such that the atom can move from this state now to this state. Okay, now according to the interpretation of the wave function, the probability of finding the atom in the state psi E sub m at time t will therefore be given as the mod of CLM 1 t squared, okay, which is the probability density function, which is the electronic charge squared, H cross squared, ZLM squared, E type Z field squared, which will now be 2 minus 2 cos omega NL, so omega T divided by L, so omega squared, where for which M is not equal to L, meaning the states are distinct, okay? Probability state L So at this point, and this is probably state M above it. Okay. Now, if we regard this as our 13th equation, then a transition probability corresponding to the probability per unit time an atom initially in state psi E L is induced to make a transition to some higher state psi E M can be defined as W L M being equivalent to d dt mod CL T squared, which is the same C squared H cross squared mod ZL squared E times Z squared to sine, once we differentiate this process, is a constant reducer, and omega ml minus omega t divided by omega minus omega plus yeah. So this now will cross this squared, so we have this, because this times all of this operation, then the negative sign is taken care of by differentiation. So we have star 14, right? Now the last factor is proportional to the Dirac delta function in the limit for t tend to infinity. Then we can take the limit of t tend to infinity such that sine omega ml minus omega t ml so omega will be the same as pi minus omega, which is our 14th equation. Okay, so it means that this property is proportional to the Dirac delta function, because near from here, near omega ml minus omega, we have this to be approximately 0, and it increases as t tends to infinity. Okay, so as t tends to infinity, it increases, and it decreases rapidly to exactly 0 at omega ml omega equal to plus or minus pi over t, which already showed in our previous classes, and to essentially 0 relative to the peak beyond. So the area under the peak between this expression is approximately equal to pi. Hence, the probability transition from the state psi, let's say psi EL to psi EM per unit time induced by a monochromatic incident wave on the atom is given as 2 pi times electronic charge squared squared Z squared, then E Z squared Dirac delta. So this is the probability transition from this state to this state, lower state to higher state. So which shows the important resonance condition that the frequency omega of the incident wave must be equal to the transition frequency omega Ln of the atom, and that transition probability is linearly proportional to the intensity of the incident wave. Okay, so this occurs at resonance. Okay. Now, if we take this as our 16th equation, we can say that this equation is a form of the Fermi Goldrow or golden rule. And since the energy, recall that the energy of a photon is the same as h cross omega, the resonance condition shows that energy is conserved in a single photon absorption process. Now, the atom can only absorb one photon of energy. The atom can absorb one photon of energy, h cross omega equal to h cross omega ml, which is the frequency of the transition, right? At a time, by being promoted from psi EL to psi EM state. Okay, that's state functions. Also, if EM is less than EL, the corresponding process corresponds to the spontaneous emission of a single photon of energy, h cross omega. While the atom drops from this state, the higher state, to the lower state, with the transition probability now given as WLM for the 2 pi electronic charge, h cross squared, ZLM squared, E times Z squared, delta omega L. So this is 17. Now, 16 and 17 are derived for the radiative transition between sharply defined energy levels induced by monochromatic waves. And in practice, the finite width of the radiation spectrum and the transition frequency range must be taken into account. And if the transition frequency is not sharply defined, either because the lifetimes of the initial and final states are finite, or because of the slight variation in the local environment of the atom in a macroscopic sample, for instance, then radiative transmission can take place over a range of frequencies. Now, the corresponding line-shaped function is not a delta function, as in these two expressions, okay? But some normalized general distribution function of the form G omega Lm minus omega bar Lm, centered on omega bar Lm1, where the integral G omega Lm minus bar omega Lm d omega is the same as 1. Now, if the energy levels of the initial and final states of the radiative induced transition are broadened because of the finite lifetime of these states, only the mechanism is called homogeneous broadening, and the corresponding line-shape function, that is, this is the Lorentzian. for which we have the homogeneous. If the energy levels are broadened because of the local environment variations, then it is called inhomogeneous broadening. Inhomogeneous broadening. And then the line shape function, say G omega Lm, so omega Lm tends to the Gaussian and not Lorentzian. Okay? Now, in the case of spontaneous emission or fluorescence, as we may call it, spontaneous emission, not stimulated this time, not coherent, it's not narrowed into some tiny spot. This is more like scattered, spontaneous emission or fluorescence. From the upper level here, the transition probability must be integrated over the transition frequency such that we have Ln equal to 2 pi squared over h cross squared ZL squared tied Z squared integral G minus omega Ln delta omega x omega n d omega. And this now gives us 2 pi d squared h cross squared ZLm squared times Z squared G omega omega n. So let's say everything here. And the fluorescence line shape, the fluorescence or the spontaneous emission line shape function G sub f of omega minus omega m is of the form G omega minus omega. Okay. Now, in the case of resonance absorption, let's say resonance absorption, from the lower energy level E sub L, and incident radiation being not a monochromatic wave, but having a normalized spectrum of the form, let's say it has a normalized spectrum of the form rho omega, and then the transition probability, as we showed in 16, must be integrated over both the distribution of the transition frequency and the incident spectrum, such that we have W Lm equal to 2 pi squared by h cross squared ZL squared E tied Z squared and integral G sub f, which is the fluorescence line function, omega Lm minus omega bar rho omega delta omega d omega Ln omega. This now is 2 pi times the electron charge squared, h cross squared, ZL squared, E times Z squared, integral G sub f from omega n rho d omega. Say this is an identification process. Hence, if the fluorescence line width is much narrower, not that broad, narrower than the spectral width of the incident radiation, then the probability of absorption, then the probability of absorption reduces to same as 2 pi squared h cross squared zl squared z tide squared or z subtentative portion. Okay. Now, if the spectral width of the incident radiation is much narrower than the fluorescence line width, for instance, then the transition probability, now here, they're saying that the spectral line width of the incident radiation is much narrower than the fluorescent line width, then the probability the transition probability will now become 2 pi e squared over h cross squared zl squared ez tide squared g sub f omega naught minus omega r, and which is our 21st equation, where omega naught is the center frequency of the incident radiation. Yeah? The center frequency of the incident radiation. Now, the 17th and 21st equation are the Fermi golden rule for radiative transitions. Okay, so now that we've covered this, let us look briefly into the selection rules, okay, considering the spectra of hydrogen and hydrogen-like atoms. Now from equation 17 and 21, which are, and are still, yeah, so we can keep 21. So equations 17 to 21 shows that the transition probability for absorption or emission process between the initial state psi EL and the final state psi EM depends on the magnitude of the induced matrix element defined by ZLN, which is the same as psi EM R Z times as the conjugate times EL R hat BR. Okay, so let's say this is our 22nd equation. Okay, you see that level of dependence shown, okay, for both absorption or emission, right? So the transition probability for absorption or emission process between these states is dependent on the magnitude of the induced matrix element, okay? Z, this is the induced matrix element. So hence, whether a particle or a particular particle transits, or let's say a particular transition is allowed or not, depends on the spatial symmetry of the wave functions of the initial and the final states of the spatial integral defining the induced matrix element, that is, these two states. So if we say, for instance, in the case of linearly polarized waves, induced transition can take place only between states of opposite polarity. Now, since the integration in this induced matrix element is to be carried out over all space, the integral should be invariant under inversion of coordinate axis. So hence, we can say that the induced matrix element is the same as psi em vector z conjugate times r vector dr is the same as under coordinate inversion to conjugate r minus r z psi el psi dr. The rest of this is 23. So by making use of the concept of parity operator, then we can say from here that we have integral parity operator, sorry, em r conjugate minus z, then parity operator el yeah. So these are 24th. Hence, the product of the eigenvalues of the parity operator corresponding to the eigenstates, EL and EM must be equal to -1. And that is this minus parameter here. And the states psi EL and psi EM must be of opposite parity. So this is one of the selection rules for the emission and absorption process. Other rules depends on other symmetry properties, such as the angular symmetry property. And for instance, we say, suppose the angular part of the initial and final wave function in our 22nd equation are given as y, l prime, ml prime, theta, phi, and psi, l, theta, phi. Then analogous to the parity condition, integration of the coordinate variable phi leads to the selection rule on the azimuthal quantum numbers ml and ml prime. And now we have delta ml, which is the azimuthal, changing azimuthal quantum number, which is ml minus ml prime equal to 0 for waves linearly polarized in the z direction. And then delta ml followed l prime equal to plus or minus 1 for right and left circularly polarized waves. So if These are 25th equation, 25th one. You can say this is our 25th two, right? And the 25th two, from this, the axis of quantization of the atomic wave function is perpendicular to the plane of polarization of the incident wave. And these selection rules reflect the conservation of angular momentum in the emission and absorption process, since the angular momentum of the circularly polarized wave is the same as plus or minus h cross, and the linearly polarized photon is an equal mixture of the photon states with the same angular momentum relative to the axis, the quantization of the atomic wave function. Now, similar consideration in theta involving associated Legendre function leads to the selection rule on the orbital quantum numbers L and L prime for dipole-induced transitions such as theta L will be the same as L minus L prime, which is the same as plus or minus 1. Note that the selection rules depend on the nature of the quantum states involved in the transition and the state of polarization of the radiation. Such rules and resonance conditions are the key considerations that determine the general feature of emission and absorption spectra of all atoms, molecules, and solids. And if we consider the discrete absorption spectra of hydrogen and hydrogen-like ions, say Z photons, in the nucleus and 1 electron, initially in the ground state, that is in the 1s state, then the selection rule, as shown in 26th equation for the orbital quantum numbers, shows that from the ground state, the atom can absorb a photon and be excited into one of the quantized NP level, where N is the same as 2, 3, 4, all the way. For the hydrogen atom, Z is equal to 1, and the corresponding wavelength of the discrete absorption line are 1 lambda 1 S, NP equal to the Rydberg constant, Z squared. So let's differentiate this, please. Just leave that Z for instance. Z squared into bracket minus 1 over N prime squared. Now, for all values of 1 less than N prime, 2, 3, 4, 5, all the way. So let's say this out to the 7th portion, where the Rydberg constant is given as the electronic mass divided to the power 4 divided by 4 pi C cubed. Now this is the Rydberg constant, and it's numerically equal to 109,737.3 per centimeter. And the longest wavelength of this series of discrete absorption line is about 121.56 nanometer in the ultraviolet. So these absorption lines and the corresponding fluorescence emission lines, that is the NP going to S state, form the so-called Lyman series of the hydrogen spectrum. So in general, the wavelength of the discrete line spectra corresponding to the transitions between other energy eigenstates of the hydrogen atom, Z equal to 1, suggests the selection rule, and this satisfies the Rydberg formula given by 1 over L prime L plus or minus 1 to the right constant squared for values of n taken for 1, 2, 3 all the way, and then n prime is greater than n. And when n is equal to 1, we have the Lyman series, and n is the same as 2, we have the Balmer series, and n is equal to 3, we have the Reeds-Paston series, and n is equal to 4, we have the Brackett series, even n equal to 5, the Font series, and so on. So now that we have discussed the transition probability, the selection rule, and the perturbation theory, so let us consider the emission and absorption process. Now, note that given the states, we have EL, EM, so let's designate this properly. So let's say we have psi EM, psi EL for our state. So emission occurs when there is a transition from a higher energy level to a lower energy level. So let's assume something like this occurs. So the atom moves from higher energy to lower energy. And then when the reverse occurs from a lower energy to a higher energy, then we have absorption. So suppose the energy of the initial state is above that of the final state. Okay, so let us say E sub L is greater than E sub M. For instance, if the hydrogen atom is initially in the 2p sub z state and the final state is the 1s state, now the term with omega ml minus omega, the denominator of the equation C Lm of t or the E ZL M E tied 1 minus epsilon J omega ml minus omega t over H cross omega ml omega. Now if we replace this with omega ml plus omega, say for emission, now the resulting induced dipole moment will lead to the applied field in a phase by pi over 2. And now if the existing field is the externally applied field of an incident wave, so the field emitted by the oscillating dipole will be in phase with and add to the incident field. Now the corresponding process is called the stimulated emission process. Okay. Now, if the only present field, or better say field, is the vacuum fluctuation field, then the emission will be the spontaneous emission process. Now, this is responsible for the luminous spectra of the atom in the excited non-equilibrium states, and the corresponding emitted field will have random phases reflecting, those of the vacuum fluorescent fields. But in our case, we are particular about lasers, and so we'll be talking about the stimulated emission process. So, light amplification by stimulated emission of radiation. Laser. So when an atom is initially in an excited state, it can be stimulated to emit a photon of the same frequency and phase as that of the incident photon at resonance. Now, if this phase of the incident photon wave is well defined, the emitted wave will be in phase with and add to the incident wave coherently. This is called the stimulated emission of radiation process. So let us consider the incident monochromatic plane wave polarized in the x direction of the form, say, E vector, the electric field vector, Z, ZT is the same as the tide, X, let's put this in bracket, epsilon J, KZ, which is the wave number, the frequency, T, plus the conjugate component, X, epsilon J, KZ, T, EX. So let's say about 29. Now, this is propagating in the Z direction in a macroscopic medium of two-level atoms with energies E1, E2, okay? Largely because of the spin, okay? Now, hence, we have E2 minus E1 over H cross will be the same as omega 2,1 approximately. And recall or note that real atoms have many energy levels, okay? And in the resonant emission or absorption process, only the initial and final states are directly affected by the interaction process. Okay, now I'd love you to take note of this, okay? Note, in real atoms, there are many energy levels, okay? Good. But not all of them are involved in the resonant emission and absorption process. So now this is one. So now in the resonance emission or absorption process, only the initial and final states are directly affected by the interaction process. So we can therefore focus only on the two relevant energy levels of the atom. Okay, say E1 and E2. Okay, so E1 and E2 in our case, or in this case. So assuming that in the presence of the incident wave, the medium is in equilibrium state, and there are, say, N2 atoms per unit volume in the upper state at equilibrium, and N1 atoms per unit volume in the lower state or level. So in the presence of the incident wave, the atom in the lower levels will absorb energy, right, or photons, and be excited into the upper level. So it means that we have this, so there's some energy here, so it gets enough energy and is excited to an upper level. Now the atoms in the upper level, so the atoms in the upper level will therefore emit photons, and once it emits the photons, then it loses all its energy, and then it drops back to the lower level. So if n sub 1 is greater than n sub 2, then there will be net absorption of photons. And if n2 is greater than n1, then there will be net emission of photons. Now, the rates of change of the populations of the atoms in the upper and the lower levels due to such photon-induced interactions are therefore given by the n sub 2 over dt be the same as minus n2 W21 plus n1 W12, and then the n1 dt be the same as n2 W21 minus n1 W12. So we can call this our equation 30, where W12 is the same as W21 as defined by our 18th and 19th equations. Now, the net rate of change of the population inversion, N2 minus N1, this population inversion is given by d dt N2 minus N1 minus 2 into bracket N2 minus N1 W2. So this is our 31st equation. And the corresponding change in the photon number, change in the photon number, NPH, per unit volume is therefore given by the NPH dt equal to N2 minus N1 W21. So this is our 32nd. Now, if the incident wave is not a monochromatic wave, and the spectral density of the incident wave is, say, rho v, where, just like we showed earlier, the integral of rho v dv give us 1. This is the density. Now, the rate of change of the volume density of light wave energy, that is the volume density of the light wave energy, will be given as the magnitude squared eta x divided by 2 in the medium, based on equation 19, and is given by d dt over n2 minus n1 4 pi squared v h cross s1 2 square rho v2. That's 3. In a real medium, there may be other processes taking place in the medium, so that the transition probability is spectrally broadened from the delta function dependence shown in 16 previously and 17 into a fluorescence line shape function, say g f of v, where, since it's also density function, the integral gf of v dv should give us 1, such that there's a probability that that particle can be found in that distribution. So in that case, if the line width of the incident radiation is much narrower than the fluorescence line width and can be considered, say, a monochromatic wave of frequency v, then the line shape function rho v21 of the radiation in this expression in 3 should be replaced by the fluorescence line shape function g f of v, which is this, evaluated at this frequency v, and then it's shown as d dt, so along here, which is n2 minus n1 4 pi squared a squared v over h cross s12 squared g sub f of v. So let's say this is 34. So converting this to the spectral rate of change of the intensity of the wave gives the spatial gain coefficient. And the spatial gain coefficient of the medium. Okay. Such that z equal to g r is equal to n2 minus n sigma st instead of okay. Consequently, sigma st is given as 4 pi squared v cross c, so 2 squared jf. In this case, c is the velocity of the wave in the medium. Okay? And sigma st is known as the stimulated emission cross-section. Now, this equation of the simulated emission cross-section shows that the electromagnetic wave will be amplified if the population inversion in the medium is such that N2 is greater than N. Okay? So this tells us that the EM wave will be amplified. Because recall that the I to Z is the same as GI equal to N2 minus N1 minus STI. So once N2 is far greater than N1, then this value increases. Then the amplitude of the wave function, will also increase. Now, if such an amplifying medium is enclosed in a suitable electromagnetic cavity in which most of the emitted radiations can be reflected back into the medium along the same path again and again for repeated amplification, even a small amount of initially present spontaneous emission can grow into a powerful coherent beam of stimulated emission at a frequency omega being approximately order omega 2. This is the basis of lasers. But according to Einstein, in Einstein B Coefficient, Einstein B Coefficient, the stimulated emission process is often characterized by the Einstein B coefficient rather than the cross-section technique shown. And there is given as B12 being the same as 2 pi electronic charge squared H cross squared X12 squared, which is equivalent to sigma ST C over HV G F of V. Say this is 37, right? Now note that Einstein A coefficient characterizes spontaneous emission. So this characterizes stimulated emission, while Einstein A coefficient characterizes spontaneous emission process. And it has to do with the fact that if an atom is in an excited state, it must eventually drop down to an available lower energy state. So if we take the two levels or the two-level atom with allow radiative dipole transition between the two levels 2 and 1, for instance, then the rate of change of the population in the upper level must have a decay term, even in the absence of any applied radiation. That is, d dt n sub 2 will be equal to negative n2 divided by tau 2, which is a decay component. So let's say this is 38. Then there is a corresponding rate of increased term for the population of the lower state, such as d dt n1 will be equal to positive n2 divided by tau 2. This is 39. Now, this relaxation time, in this case, relaxation time, tau 2, gives the radiative lifetime. This gives the of the level 2. Okay? And if there is no other lower energy level, then the atom can decay. So the corresponding relaxation rate, tau inverse 2, is by definition the Einstein A coefficient. Okay, this is the Einstein A Coefficient, A21. Now, if there are n levels of lower energies to which the atom in a higher energy level, L, can decay, then the total radiative decay out of the Lth level is the same as A sub L, being the same as summation ALM for L equal to 1 n. And the radiative lifetime of the Lth level, tau L, will now be the same as A sub L to the power. Now, Einstein A coefficient is directly related to the Einstein B coefficient for the same transition. And the relationship between both may be found by considering the situation where the two level atoms is in thermal equilibrium, okay, with the black body radiation. So the corresponding rate equation for the population in level 2 in the presence of the black body radiation is given by dt n2 minus n1, which is minus 2 a21 n2 minus 2 b21 n2 n1 will be v21. Okay? Now this is going to give us minus 2 a21 n2 minus 2 b21 n2 minus n1 okay. 8 pi h b21q divided by cq by 1 over epsilon h b21 is the thermal energy, kT. So, right? This is 41. In thermal equilibrium, say at temperature T, we know that d dt n2 minus n1 is the same as 0. And the ratio of the population in the upper and lower energy levels is determined by the Boltzmann factor minus HV21 divided by thermal energy, kT, which is the Boltzmann factor, right? So if we assume that we have an oscillator strength, F12, related to the cross-section for absorption, rho AB, given by AB is the same as squared over 4 epsilon naught, the electronic mass times C, 2 V, then I is squared over 2 epsilon naught C F12. So in this case, E is the electronic charge, M sub E is the electron mass, V is the normalized distribution, function, frequency, by omega, 5 omega is the normalized distribution, function in angular frequency, right? And then the Einstein A and B coefficients in terms of a single oscillator strength associated with the specific atomic spectral line are given by A21, the same as 2 pi, B21 squared over epsilon naught, E CQ G sub 1 G sub 2 1 2 E21 squared electronic charge 4 so the electron mass one constant V21 G1 G2 V2 and then B12 with the same as electronic charge squared for epsilon naught electron mass V2. So let's say this is 45, this is 46, this is 47. Now, for the one, and by comparing 45 and 46, the ratio of the Einstein A and B coefficients can now be given as A21 over B21 to be equal to 2 pi B21 squared epsilon naught E CQ G 1 over G2 2 times 4 epsilon naught to 1 squared G2 G1 2. So all of these will cross, right? Then epsilon cross, electronic mass will cross, then electron charge cross. So what we now have E21 8 pi h V21 cube divided by CQ. And this shows that the B coefficient or the induced dipole matrix element, say squared S21, may be determined from the A coefficient. This can equally be determined experimentally from the measured corresponding radiative lifetime of the atom in level 2. So the B or Einstein B coefficient determines the stimulated emission cross-section and hence the gain coefficient in the laser. And note that lasers amplify electromagnetic waves at wavelengths ranging from radio to ultraviolet and X-rays. They were originally called maser because the first unit amplified microwave. Okay, call this microwave amplification by stimulated emission of radiation. And the maser is a device that emits coherent electromagnetic waves through amplification by the stimulated emission of radiation. And masers uses stimulated emission in the stream of energized ammonia molecules to amplify the microwave. You should note that both masers and lasers are based on the concept of stimulated emission of radiation. As we mentioned earlier, in the process of stimulated emission, an electron goes to a lower energy level due to an interaction with the electromagnetic wave. And depending on the medium used, masers may be classified as atomic beam laser or gas maser. We have solid state maser, and we also have the dual noble gas maser. And masers are used in very low noise microwave amplifiers, atomic clock, spacecraft communication, and so on. And for laser, we have the classifications as solid laser, we have gas laser, we have liquid laser, we have the chemical laser, then we have metal vapor laser, and then we have the semiconductor laser. And know that lasers emit light which is coherent, and the spatial coherence allows the laser to be focused on a tiny spot. And lasers are used in communication systems, heat treatment, computing devices, welding and cutting, surveying and ranging, and a host of others, including medicals. And know that laser is a device which emits light by the process of optical amplification based on the stimulated emission of radiation. So masers produces amplified microwave, while laser produces amplified light, all based on stimulated emission. So we stop for now and hope to see you in the next class. Bye for now.